You know, the era of using AI to just like save a few bucks on customer support, that's over. It's completely over.
Oh, absolutely. The coupon clipping phase is dead.
Right. Stop clipping coupons. I mean, if you're a product owner and you're treating artificial intelligence purely as a cost center, like it's just this mechanism to shrink your way to greatness, you are already falling behind.
Yeah, because you really can't shrink your way to greatness. It just doesn't work.
Exactly. The companies that are actually pulling ahead in 2026, they aren't sitting around asking where AI can trim a margin. They're asking where it can create a totally new line item on the invoice.
A completely new revenue stream.
Yes. And that's why you're here. You're a builder. You are ambitious. So, over the next 30 days, we are going to dive into how to turn your AI strategy into actual tangible capital.
That is the definitive line in the sand right now. Honestly, welcome to the deep dive, everyone. We are operating with a very specific mission today.
A highly tactical mission.
Very tactical. We're laying out a rigorous chronological 30-day plan. In 1 month, you are going to conceptualize, engineer, refine, and launch an AI-driven product feature.
And not just to see if it works, right?
Right, no. We are pointing all of this toward one ultimate metric, and that is testing actual customer willingness to pay.
Because we are building toys here. We are not doing research just for the sake of, academic research. We're building a revenue engine.
Exactly. And to get you there, we've pulled together this really elite arsenal of source material for today's deep dive.
It's a gold mine. We're going to synthesize a whole manifesto on AI revenue generation, plus a comprehensive technical primer on deep learning.
Which is crucial, yeah. You know how the engine works.
Right. And then we have these elite prompt engineering frameworks, including Google Gemini's internal best practices and this really highly sought-after 5-layer visual framework.
We also have a dedicated lab on simulating AI experts, basically using AI to ruthlessly red team your own ideas.
Which is so cool. And finally, we've got an exhaustive, like almost forensic guide to scrubbing your final product of all those lazy, cringeworthy AI tells.
Using the industrial design philosophy of Dieter Rams, no less.
Yes. So over the next 30 days, you aren't just like bolting a generic chatbot onto your app. You are shifting your entire business model from a cost story to a revenue story.
So let's just get right into the trenches. Day 1 through day 7, this is phase 1, the structural shift and ideation.
Okay, so the manifesto we're working from makes this really critical observation about the legacy mindset of the early 2020s versus where we are now in 2026.
Right, because for the last few years, the mandate from the CFO has been strictly operational.
Defensive, right. Like deploy the model, reduce headcount in the support tier, automate the back office routing.
Yeah, just shave 10% off operating expenses and call it a day. It was a totally defensive posture.
But structural shifts happen when technology moves from defense to offense. And the sources explicitly state that AI is no longer just the invisible plumbing behind the scenes.
It is the product itself.
Exactly. So the manifesto outlines 3 very specific practical applications where product owners can extract massive new value.
The first one is embedding copilots directly into core workflows. And we should clarify, this isn't just a conversational bot floating in the corner of your screen.
Oh yeah, not the annoying little pop-up guy.
No, this is software that actively participates in the work.
Let's ground that in a reality that you, the listener, might actually face. Say you build architectural drafting software.
Okay, great example.
The legacy approach is giving the architect a blank canvas and some really highly optimized line tools. Good luck, right?
Right. But the new application is an embedded copilot that instantly drafts the foundational structural grid based on the local zoning codes you just uploaded.
It does the grunt work instantly.
Precisely. And that leads perfectly to the second application. Generative design tools that completely collapse the customer's time to output.
Time is money.
Always. If your B2B client used to spend, say, 3 agonizing days designing a supply chain schematic, and your new generative feature allows them to achieve a superior schematic in 3 hours.
I mean, you haven't just saved them time. You've fundamentally increased their throughput. Their profitability just skyrocketed.
Exactly. That is immense quantifiable value that they will pay for.
Which naturally leads to the third and honestly most important application for our 30-day mission. Layering these AI features into existing products to justify premium pricing.
The direct upsell.
Yes. You are looking for that one SKU in your portfolio where an AI capability lets you introduce a higher pricing tier or significantly increase your average revenue per user.
Because, look, internal efficiency compounds really slowly. Saving a few $1,000s on cloud compute or support tickets. That takes quarters to show up meaningfully on a balance sheet.
Right. But a premium revenue generating feature that reshapes your market perception overnight. It completely changes your pricing power.
It's the difference between aggressive couponing and opening a new storefront.
I love that analogy. Clipping coupons feels great when you save 50 bucks on server costs, but you can only cut so deep, you eventually hit bone.
You do. Opening a highly profitable new storefront in a bustling neighborhood, that is how you build new capital.
But, and this is a big bone, but before you break ground on that storefront, before you allocate developer time or write a single line of code, you have to know if the neighborhood actually wants what you're selling.
Which brings us to the second half of week 1, simulating your expert board of directors.
This part is
It
fascinating.
really is. This is where we leverage a concept from the Google DeepMind sources called GEMs.
Right.
These are custom AI experts that you instruct to adopt hyper-specific personas. You are essentially spinning up a boardroom of the most ruthless, brilliant minds imaginable to stress test your revenue idea in minutes.
See, I look at this and I immediately see a massive vulnerability for confirmation bias.
Oh, for sure,
Yeah.
if you aren't careful.
Like, if I'm the product owner and I'm writing the prompt for my simulated board of directors, the temptation to create a massive echo chamber is just huge.
Right, you pitch your brilliant idea for a premium AI upcharge.
And the bot I program just pats me on the back and says, "Incredible idea, sir. Go build it immediately. You're a genius."
And that is the exact trap that kills early-stage features. It's why the system prompt for these gems requires such incredibly tight constraints.
So how do we fix it?
Well, our sources are very clear. You never, ever ask the gem for validation. You explicitly program it to act as a hostile red team.
I love the term hostile red team.
Right, you instruct it. You are an incredibly cynical, financially rigorous chief financial officer. Tear this premium pricing model apart.
Give me the worst case scenario.
Exactly. Tell me exactly why our enterprise clients will absolutely refuse to pay for this. Point out the hidden operational costs that we are completely ignoring.
So you're basically demanding friction.
You demand absolute brutalism from the AI. You force the model to look at the idea through a highly critical lens.
And you could do this for multiple roles, right?
Oh, yeah. Another gem might be programmed as a deeply skeptical product marketing manager who dissects exactly why your value proposition sounds just like your competitors.
By building that accountability into the ideation phase, you ensure the idea is bulletproof before day 7 is even over.
Exactly. So you survive the simulated boardroom, the red team couldn't kill your idea, the value proposition holds up, and you have your target feature mapped out.
Awesome. But if you walk into a client pitch, propose a 50% premium for this new AI capability, and the client looks at you and asks, "Okay, but how does your system actually arrive at these insights?"
Yeah, you can't just shrug and call it magic.
The moment you say magic or, it's just an algorithm, your pricing power just evaporates.
Completely. The client's procurement team will smell blood in the water. They'll immediately classify your product as a generic API wrapper and demand a massive discount.
Which means we have to open up the engine. We have to know how it works.
Which takes us to days 8 through 14. This phase is entirely dedicated to technical fluency.
You have to understand the transition from traditional machine learning to deep learning, and you have to understand it deeply enough to actually defend it in a boardroom.
Our technical primer frames this evolution brilliantly, I think. It reminds us that technological innovation is almost always a direct response to the friction of human inconvenience.
Right, like we moved from writing physical letters to telegraphs because weeks of transit time was inconvenient.
And we moved from telegraphs to video calls because lacking visual nuance was inconvenient.
So deep learning emerged specifically to solve the crippling bottlenecks of traditional machine learning.
Let's unpack the mechanics of that bottleneck, because it's important. If we look at traditional machine learning ML, the primary friction point is manual feature engineering.
Okay, what does that actually look like in practice?
Imagine you're building a B2B product that analyzes factory assembly lines. Okay? It needs to sort defective mechanical parts from healthy ones using a camera.
Okay, pretty standard industrial use case.
Right. In traditional ML, a human programmer has to sit down and explicitly define the mathematical rules for what a healthy part looks like.
They literally write the code.
Yes. They write code dictating the exact dimensions, the color threshold of the metal, the weight tolerance.
But the real world is messy. Like, what happens when the lighting in the factory changes and it casts a weird shadow on the part?
Or what happens when a part is structurally perfectly sound but just has a harmless surface scratch.
The traditional ML model shatters. It just completely fails because it struggles with any subtle variations that fall outside its rigid, manually programmed rules.
And it fails spectacularly when you feed it highly complex, unstructured data.
Because you can't easily sit down and write a simple mathematical rule for, like, the acoustic profile of a failing turbine.
Or the visual texture of a microscopic hairline fracture. It's impossible to hard code that.
And this is exactly where the paradigm shifts to deep learning. Deep learning doesn't ask you for the rules.
No, it learns the context directly from the raw data. It completely bypasses that manual feature engineering bottleneck.
So you don't craft the rules at all.
You feed the DL model massive, staggering volumes of data. Thousands of audio files of failing turbines, tens of thousands of images of parts in every conceivable lighting condition.
It just has this insatiable hunger for data volume.
And through that volume, it grasps complex, nonlinear patterns that a human programmer could never manually hard code in a million years.
But, and this is a big caveat, there's a strategic trade-off here that product owners have to navigate. It's the tension between interpretability and performance.
Ah, yes. The core dilemma of the black box.
Explain that for us.
So traditional ML offers incredibly high interpretability. If your sorting machine rejects a mechanical part, you can look at the ML code and see the exact line of logic that triggered the rejection.
Like error. Weight exceeded tolerance by 0.2 grams.
Exactly. You know why it did it. Deep learning, on the other hand, gives you vastly superior performance and accuracy on unstructured data, but it acts as a black box.
You know, the output is highly accurate, but you have very low interpretability regarding exactly why the neural network made that specific connection.
Right. And to defend that black box to a client, we need to understand its biological mimicry.
The primer dives into neural network architecture here, and it starts with a structure inspired by the human brain. We're looking at layers.
You have three primary structures. First, the input layer. This receives the raw, unstructured data. Think of it as the raw pixel values of an image or the frequency bands of an audio file.
Then you have the hidden layers.
Yes, this is the dense, complex middle where the actual computation and pattern recognition occur. It's where the magic happens.
And finally, you have the output layer, which delivers the final prediction or classification.
Let's say our product feature is a predictive engine for classifying customer support tickets into 10 different severity categories.
Okay.
That means our output layer explicitly has 10 neurons, one for each category.
So let's define these components mathematically, starting with the neuron itself, because people hear neuron and they think biology.
Right, but a neuron in this context is just a fundamental mathematical unit that holds a value. It's just a number.
But neurons don't exist in isolation. They're connected by weights.
Yes, a weight is a numerical value assigned to the connection between two neurons, and it represents the importance of a specific feature.
If we translate that back to our customer ticket classifier, maybe the system looks at the metadata of the ticket. The customer account size feature might be assigned a very high weight.
Because it's important.
Right, while the time of day the ticket was submitted might have a much lower weight.
Exactly. The network mathematically prioritizes the signals based on those weights. And then we introduce a bias.
What's the bias do?
A bias is an additional constant value added to the calculation to correct potential systemic inaccuracies and shift the activation threshold. It basically ensures the model doesn't just pass zeros through the network and stall out.
So inside every single neuron across those massive hidden layers, the core math is shockingly straightforward.
It really is. The neuron value equals the sum of the inputs multiplied by their respective weights, plus the bias.
It's just simple algebra. Sum of inputs times weights plus bias.
But the scale is what makes it powerful. It's billions of these simple calculations firing simultaneously.
The real question, though, is how this static math actually learns to get smarter. Like, how does it adapt?
That is the training mechanism, and it operates through a continuous cycle of trial, error, and feedback.
It begins with a forward pass, right?
Yes. The raw data flows from the input layer, propagates through all the hidden layers doing that algebra, and arrives at the output layer to make its initial prediction.
And because the initial weights are basically randomized, that first prediction is going to be completely wrong.
Utterly wrong. It looked at a highly urgent enterprise outage ticket and classifies it as a low-priority password reset.
So the system has to measure exactly how wrong it is. We calculate the loss or the error.
Our technical sources emphasize a common metric for this called mean squared error, or MSE.
How does that work?
You take the model's predicted value, subtract the actual ground truth value, and square the difference
Why square it?
to ensure negative and positive errors don't just cancel each other out. And then you average that across your data.
As a product owner, you look at MSE not just as a math problem, but as a financial liability.
Oh, definitely. If your MSE is high, your AI is actively making bad decisions that cost your clients money.
The entire goal of training the model is to minimize this error, driving it down until it reaches what they call the local minima.
Right, the mathematical valley where the error is as low as it can possibly go.
And to reach that valley, the network executes backpropagation, the backward pass.
This is the genius of it. Once the error is calculated at the output, that error signal flows backward through the entire network.
Like a shockwave.
The algorithm uses calculus, specifically the chain rule, to determine exactly how much each individual weight contributed to the final error.
So it points the finger at the weights that messed up.
Exactly. It then tweaks those weights slightly so that the next time the data passes through, the prediction is a tiny bit closer to the truth.
It's the ultimate game of hot and cold. The network takes a guess, the loss function screams freezing cold, and backpropagation nudges all the dials toward warm.
And it does this millions of times.
Millions. And as the product owner overseeing this, you aren't manually turning those individual dials, obviously. But you do control the master controls, the hyperparameters.
Yes, hyperparameters are the levers that govern the training process itself. And they have massive operational and financial implications.
Let's look at the epoch first.
An epoch is one complete cycle of passing your entire training data set through the neural network.
So if you set your epochs too low, the model just doesn't learn enough.
But if you set them too high, you're burning expensive GPU compute time for diminishing returns.
Yeah.
You're just wasting money.
Then you have the batch size. You don't want to process a data set of 5 million images all at once.
No, you would instantly melt your cloud infrastructure, and your server bill would be catastrophic.
So you process the data in smaller chunks or batches. You calculate the error for a batch, update the weights, and move to the next.
It's a mechanism to save computation time and manage memory effectively.
And the most delicate dial of all is the learning rate.
The learning rate controls the step size, basically the aggressiveness with which the model updates its weights during backpropagation.
What happens if it's too high?
If your learning rate is set too high, the model takes massive leaps. It constantly overshoots that local minima valley of lowest error. It just bounces wildly back and forth.
But if you set the learning rate too low, it takes tiny, microscopic steps.
Right. The model will eventually find the lowest error, but it might take 3 weeks of continuous GPU processing to get there.
So you're constantly balancing mathematical precision against your AWS bill.
Exactly.
Now, I want to stop you here because there is a massive conceptual friction point we have to resolve for the listener.
Okay, let's hear it.
You said earlier that deep learning grasps complex, curvy, nonlinear data patterns that traditional ML can't handle. But the core math equation you gave me inside the neuron multiplying inputs by weights and adding a bias, that is fundamentally linear math.
It is.
It's literally the equation for a straight line. So if you stack 100 layers of straight lines, mathematically, you just get one giant straight line. How does the network physically bend the math to understand nonlinear reality?
That is the exact paradox, and the solution is arguably the most important mechanism in the entire architecture. Activation functions.
Activation function.
Think of these as mathematical gates sitting at the very exit of every single neuron. Their entire purpose is to warp the linear math, standardizing the output ranges, and deliberately injecting nonlinearity into the network.
Because without those gates, the whole 100-layer deep network just collapses mathematically into a basic linear regression.
Exactly. The deep architecture becomes utterly useless without them. So we introduce specific types of gates. The workhorse of the hidden layers is ReLU.
The rectified linear unit.
Yes, ReLU. It is beautifully simple. It looks at the incoming mathematical value. If the value is negative, ReLU turns it to 0.
Just flat zero.
A flat 0. If it's positive, it lets the value pass through unchanged.
Right, really? Just turning negative numbers to 0 is enough to bend the math.
Just that simple act of snapping the line at 0 introduces a bend, a nonlinearity, that allows the network to start modeling incredibly complex shapes when combined across millions of neurons.
That's wild.
It is. And for the output layer where we actually need a final decision, we look at different gates, like the sigmoid function.
How does sigmoid work?
Sigmoid is crucial for classification tasks. It takes whatever wild, massive number the network spits out and mathematically squeezes it into a tight range, strictly between 0 and 1.
Oh, which mimics probability.
Exactly. If your BDB feature is predicting whether a client will churn and the output neuron fires at 0.88, your software can interpret that as an 88% confidence score that the client is leaving.
That's so elegant. There is also the TON function, right?
Yeah, TON is similar to sigmoid, but stretches the range from -1 to +1, allowing for stronger gradients.
Okay, so our technical primer specifically isolates a different type of architecture for products dealing with computer vision.
Yes.
If your 30-day plan involves building that generative architectural drafting tool we discussed earlier, standard dense layers aren't going to cut it.
No, you need convolutional neural networks, or CNNs.
CNNs, why are they better for images?
They are the undisputed gold standard for image processing because they understand spatial hierarchy.
Spatial hierarchy.
Think about it. A standard neural network flattens an image into a single massive line of pixels.
Which destroys all the context.
Exactly. It destroys all the spatial relationships between a corner, an edge, and a texture. A CNN processes the image exactly as a computer natively sees it, as a two-dimensional grid of pixels.
Right, where every pixel is a numerical value, like 0 is pitch black and 255 is bright white.
The CNN sweeps over this grid using a process called convolution, applying small filters to detect edges and shapes. But the real magic is a layer called max pooling.
Max pooling, let's explain this.
I want you to imagine looking at a highly detailed, really noisy architectural blueprint.
Oh, okay, I see.
And then squinting your eyes.
I was thinking.
Max pooling systematically moves across the image grid in small chunks, say a 2x2 square of pixels. It looks at those 4 pixels, extracts only the highest numerical value, the brightest, most dominant feature, and completely throws away the rest.
And it's purposefully downsampling the data.
Yes. It strips away all the background noise, the texture of the blueprint paper, the minor smudges, and mathematically isolates only the heavy, load-bearing walls.
It distills complex visual noise down to its most critical, essential features.
Our sources use the Fashion MNIST dataset as an example. It's this massive library of clothing images. You take those raw pixel values from 0 to 255 and you normalize them by dividing by 255.
Which means all the data sits neatly between 0 and 1.
Yes. Normalization drastically speeds up the learning rate because the network isn't struggling with massive numerical swings.
And then you use max pooling to isolate, like the collar of a shirt or the heel of a shoe.
And once you've extracted those pure features, you feed that condensed data into a standard dense neural network to make the final classification.
The primer also mentions a really fascinating technique used during training called dropout.
Dropout is a structural safeguard against memorization.
How does it work?
During the training phase, a dropout layer will randomly shut off or drop a certain percentage of neurons in the network, perhaps 20% of them on any given pass.
Okay, from a product owner's perspective, randomly crippling your own highly optimized engine sounds insane.
Yeah.
Why introduce deliberate failure?
To prevent the catastrophic failure of overfitting.
Overfitting.
Overfitting happens when your model trains so aggressively on your specific data set that it essentially memorizes the data.
Including all the useless background noise and anomalies.
Yes. It performs flawlessly in the lab, but the moment you launch it to a real customer who uploads slightly different data, the model completely breaks.
It's kind of like corporate restructuring.
How so?
Like if you're running a critical department and every single day you randomly send 20% of your staff on mandatory leave.
Ah, I see.
The remaining team members are forced to learn how to do everything. They have to understand the core mission. They cannot become hyper-reliant on one single superstar employee to carry the whole load.
That's a great analogy. By randomly dropping neurons, you force the entire network to become robust and generalized.
It creates a resilient architecture, and that brings us to the practical deployment.
Right, because by the end of day 14, you don't need to be able to code this from scratch.
An AI can write the Python syntax for you.
Exactly. But you need to understand the intuition behind the TensorFlow workflow.
TensorFlow is the primary library you'll use, and the workflow is basically 5 clear steps.
Step 1. Define the architecture. You tell it how many hidden layers to build and what activation functions, like RealU or sigmoid, to use at those gates.
Step 2. Set the optimizer.
The sources highlight Atom, which is a highly efficient algorithm for adjusting those learning rate dials during backpropagation.
Step 3. Set the loss function, like our mean squared error, to define what wrong mathematically looks like.
Step 4. Fit the model. This is where you actually pour the training data in and run the epochs.
And step 5, evaluate. You take completely unseen data the model has never trained on, and you test it to see if it actually learned the underlying patterns or if it just memorized the answers.
And the primer insists on one vital operational detail here.
Right.
Always set a random seed.
What exactly does the seed do?
Well, the initial weights in a network are random, right?
Right.
If you run your code today and get a great result, but run it tomorrow and the new random starting weights lead to a terrible result.
You have totally unstable product.
Exactly. Setting a random seed forces the computer to generate the exact same random starting numbers every single time. It guarantees reproducibility.
Which is absolutely essential for enterprise software.
And with that, the black box is open. Day 14 concludes.
You understand the engine, you understand the financial levers of epochs and batch sizes, and your deep learning architecture is sound.
Which brings us to the pivot. Days 15 through 21. Phase 3. Building the prototype and the go-to-market assets.
This is where so many technically brilliant product owners fail.
They really do. You could have a phenomenal neural network under the hood, but if your marketing assets, your landing pages, and your prototype UI look like generic, low-effort AI slop.
No enterprise client is going to pay a premium for it.
Never. The aesthetic quality signals the engineering quality to the buyer.
To command a premium, the outputs have to be pristine, and this is where we deploy the elite prompt engineering frameworks.
The source document addresses this head-on. It notes that when AI-generated images look artificial, plastic, or fake, it is rarely a limitation of the underlying diffusion model.
It is almost always a symptom of lazy, low-effort prompting.
Yes. If you give a model a vague prompt, its mathematical architecture forces it to regress to the mean.
Meaning what?
It aggregates millions of images and gives you the most statistically average, safest, and therefore most boring visual possible.
A lazy prompt is basically like walking into a Michelin star restaurant, sitting down and just ordering food.
Exactly. You will technically receive what you asked for, but you are abdicating all control. And you certainly aren't getting the chef's tasting menu.
To get the tasting menu, you have to eliminate the AI's need to guess. And that brings us to the 5-layer prompt framework for studio quality visuals. It's designed to lock down every single variable.
Layer 1 is subject and action. You never just ask for a professional woman.
Too vague.
Way too vague. You provide explicit demographic and physical constraints. A 35-year-old Japanese female executive wearing a tailored navy blazer analyzing a transparent data projection.
Layer 2 is environment and lighting. This is the layer that really separates amateurs from professionals.
If you leave lighting up to the AI, it defaults to a flat, artificial plastic glow that immediately triggers the uncanny valley.
You have to dictate the lumen environment. Cinematic lighting, soft golden hour sunlight filtering through a frosted glass window from the upper left, casting dramatic but soft shadows.
Layer 3 elevates the image from a mere digital render to a photograph, camera, and lens.
You literally use actual optical physics to control the AI's generation.
By prompting, shot on a Canon EOS R5 with an 85mm f1.4 lens, you aren't just dropping brand names to sound cool.
You are mathematically instructing the AI to mimic the specific focal length and shallow depth of field of that hardware,
which organically blurs the background and draws sharp focus to your subject.
Layer 4 is color and texture. You define the palette and the tactile reality.
You instruct it to use warm amber and deep charcoal tones.
And you demand specific textures like matte finish on the blazer, dewy skin texture, visible film grain.
That physical texture is what shatters the plastic AI look.
Finally, layer 5, style and quality tags. You lock in the aesthetic with industry-specific terminology.
High editorial tech photography, 8K ultra-realistic architectural digest style.
When you stack those 5 layers together, you stop generating cheap AI artifacts and you start generating proprietary brand assets.
That locks down the visual aesthetics. But what about the strategy, the copy, the underlying logic of the marketing?
For that, we turn to the Google Gemini 4-part framework.
Text models operate differently than diffusion models, but the principle of constraint remains exactly the same.
The Gemini structure is incredibly clean and modular. It's 4 parts: persona, task, context, and format.
You mandate who the model is, exactly what it needs to output, the background data it needs to consider, and the precise structure of the final deliverable.
And the Gemini guide emphasizes the 3 C's: be concise, be clear, and be consistent.
The consistency aspect is huge for product owners.
Let's talk about that.
If you are feeding the AI your proprietary data, you cannot alternate your vocabulary. If you call your data structure a matrix in paragraph 1, a spreadsheet in paragraph 2, and a data tab in paragraph 3,
You shatter the model's contextual mapping.
it gets completely confused about what entities relate to what. Pick one term and lock it in.
The framework also demands iteration. You do not treat the prompt box like a Google search engine where you hit enter and just pray for a finished product.
You have to break complex strategic tasks into sequential steps.
Like if you're designing your launch strategy, prompt the AI to generate the core guiding principles first.
And once you review and lock in those principles, then you write a second prompt asking it to draft the execution plan based strictly on the approved principles.
But the most dangerous technical pitfall when generating text assets is mismanaging the context window.
The context window is the model's short-term memory capacity within a single chat session. It holds the prompt, the output, and the recent history.
Right. Imagine you're using a chat session to rigorously debug the Python code for your new deep learning feature. You spend 2 hours feeding it error logs and technical specs.
Okay, heavy technical context.
And then in that exact same chat window, you ask it to write a breezy, compelling LinkedIn post announcing the product launch.
Oh, it will completely hallucinate the tone.
Totally.
It will cross-contaminate its memory, pulling dense technical jargon and error codes right into your marketing copy.
You must forcefully manage the context window. When the task changes, start a completely new blank session. Prevent the AI from dragging irrelevant historical data into your new strategic task.
Applying these frameworks, Phase 3 culminates in building platform-specific go-to-market strategies.
We take the deep learning engine we built in Phase 2, and we market it using the constraints from Phase 3.
The sources outline precise architectural prompts for different channels.
If your target is B2B enterprise clients on LinkedIn, your constraint is 150 to 300 words.
You prompt the AI to lead with a contrarian hook, challenging the cost-saving AI mindset, maybe. The body must avoid paragraphs entirely, utilizing bullet points and vivid analogies.
Like Castle Security or something.
Right. And it must conclude with a hard business takeaway and a definitive call to action.
But if you're pivoting to X, the constraint shifts to the viral thread format.
The prompt demands a high-friction hook, followed by a sequence where every single post contains exactly one mind-blowing fact.
Perhaps explaining how max pooling strips away noise.
Constrained to 280 characters, utilizing strategic emojis as visual line breaks, and maintaining an aggressively punchy tone.
And for Instagram, you aren't asking the AI for a caption. You prompt the AI to architect a visual carousel script.
You tell it. Slide 1 must be a massive text hook. Slides 2 through 5 must contain one digestible sentence of text paired with an explicit visual generation prompt for the design team using the 5-layer framework.
And slide 6 is the save CTA, plus hashtags.
So day 21 arrives. You look at your desk.
You have a structurally sound deep learning prototype. You have world-class studio-quality visual assets. You have a meticulously prompted multi-channel launch strategy.
You feel incredible. You think you are ready to launch.
But you are not.
You are absolutely not, because we are entering Phase 4, days 22 through 29.
The Dieter Rams Polish and the anti-AI Turing test.
This is where the process becomes ruthless.
Before day 30, you must subject the entire product experience, every onboarding tooltip, every error message, every line of marketing copy, every automated email to a forensic scrub.
You must hunt down and eradicate the lazy AI hallmarks. We have to understand the psychological stakes here.
Paint that picture for us.
If a procurement manager is evaluating your software for a $100,000 enterprise contract and they smell lazy AI in your user interface or your white papers,
The illusion of premium value shatters instantly.
their willingness to pay drops to zero. They will view you not as an innovator, but as an opportunistic wrapper over a cheap API.
To execute this scrub, our sources introduce a system prompt inspired by the legendary Braun industrial designer, Dieter Rams.
Banger, Eber, Besser. Less but better.
We are applying the austere principles of mid-century industrial design directly to the AI's textual and functional outputs.
This system prompt enforces 5 non-negotiable constraints on the model.
First constraint, utility first. Prioritize function over form ruthlessly.
The AI must answer the core problem immediately in the first sentence and physically eliminate any text that does not directly aid the user's comprehension.
Second, restraint and neutrality. The AI must understand it is a utilitarian tool, not a human companion.
You explicitly ban all conversational filler, all emojis, and all enthusiastic affirmations.
No more outputs that start with "certainly, I can absolutely help you with that great question."
Ugh, yes. And no decorative, moralizing summaries at the end of a factual response. Pure neutrality.
Third is absolute clarity. Make the underlying logic entirely self-explanatory. Break down complex, deep learning architectures without dumbing down the actual science.
Fourth is honesty and precision. If a specific feature has a known limitation or a high error rate, state it plainly.
Do not hide it behind marketing fluff. In enterprise software, accuracy is the ultimate form of respect for the user.
And fifth, timelessness. Ban the use of hype cycle buzzwords. Rely on durable, foundational principles that will still make sense in 5 years.
But the philosophical constraints are only half the battle. The most actionable part of Phase 4 is the exhaustive encyclopedic guide our sources provide on detecting AI text.
This is our forensic hit list. We are purging the AI idiolect.
Let's start with the vocabulary, the banned words list. If you see these words anywhere in your product copy, delete them immediately.
Delve.
Tapestry.
Vibrant.
Crucial. Showcase. Testament.
Pivotal. Underscore. Seamless.
Pumpkin. Elevate.
Landscape.
We are drowning in these words across every digital platform right now.
It's exhausting, but what is truly fascinating is why the AI overuses them. It isn't random.
No, it is a mathematical phenomenon called statistical regression to the mean. I need you to unpack the mechanics of this because it explains so much.
Well, large language models do not think. They use vast vector spaces and statistical algorithms to predict the highest probability next token or word based on their training data.
Right, and these models were trained on the entirety of the internet.
Think about how the internet describes famous people, historical events, or major corporate product launches. The language is overwhelmingly saturated with generic, self-important, positive-sounding adjectives.
It's all marketing copy and PR releases.
Exactly. So when you ask an AI to write a paragraph and it searches its statistical weights for the next word, a highly specific, unusual, nuanced fact has a very low statistical probability of being selected.
Because nuance is rare in the training data.
But generic, positive fluff has a massive statistical probability.
The Wikipedia guide source has a hilarious and perfect example of this. It notes that a highly specific factual description of a person, like calling them the inventor of the first train coupling device, will get smoothed over.
And replaced by the AI with a phrase like, a revolutionary titan of industry.
The math literally blurs the specific facts into generic fluff.
The source uses a brilliant visual metaphor. It compares it to shouting louder and louder that a portrait shows a uniquely important person, while the portrait itself is fading from a sharp, high-resolution photograph into a blurry, generic charcoal sketch.
The subject becomes mathematically less specific, but rhetorically more exaggerated.
And that is exactly why everything an AI writes becomes a rich tapestry or a pivotal landscape. It's just statistical smoothing. It's the safest, most average guess.
We have to purge it. What is the next tell on the hit list?
Copilot's avoidance.
Okay, what is that?
This is a subtle but incredibly strong indicator of machine-generated text. For some reason, embedded in their reinforcement learning, LLMs seem to aggressively avoid using basic to-be verbs like is or are.
Right. Instead of writing a normal human sentence like, the gallery is an exhibition space, the AI will write, the gallery serves as an exhibition space.
Or it boasts A or it features A.
It is trying so hard to sound dynamic and sophisticated that it ends up sounding entirely robotic.
We also must watch for the phenomenon of elegant variation.
Oh, this one drives me crazy.
Generative AI models have a repetition penalty parameter built into their core code. It is an explicit instruction designed to prevent the model from looping or stuttering.
Which makes sense in theory.
But the side effect is that the AI is mathematically terrified of reusing the same noun too often in a paragraph.
So if it is writing a case study about a CEO, instead of just using her name or saying she, the AI will cycle through increasingly bizarre synonyms to avoid the repetition penalty.
It will call her the executive, then the key player, then the protagonist of the boardroom.
The sources highlight an example regarding an artist named Yankelevsky. The AI was so desperate to avoid repeating the word artist that it started calling his group nonconformist artists. Then it pivoted to discussing their creativity.
And finally described their work as adding to the rich tapestry of artistic expression in the vibrant cultural landscape.
It is exhausting, bloated copy. It is the definition of artificial.
Beyond the vocabulary, we must examine the structural tics. These are the paragraph-level patterns that scream AI. The first structural tick to scrub is superficial analyses.
AI loves to attach an ing present participle phrase at the very end of a completely mundane factual sentence to make it sound profound.
Yes. The transit station has supported various passenger trains, contributing to the socioeconomic development of the region.
Or, these bronze statues are now housed in the National Museum, highlighting their enduring historical and pedagogical significance.
It is as if the AI is insecure about the sentence it just wrote and feels a desperate need to justify why the fact matters.
That ties directly into the next structural tick: undue emphasis.
LLMs will take an incredibly boring, mundane topic and puff it up with unearned gravity.
The sources note an example where an AI was asked to write a brief summary about a local shopping mall's Instagram account.
And the AI wrote, Forum Kochi has consistently demonstrated excellence in digital promotions, with high-quality, engaging, and impactful video content playing a key role in its outreach.
It's a mall Instagram account posting about a shoe sale. It's not the moon landing.
It's undue emphasis. Then we have to hunt down negative parallelisms.
Not only X, but Y.
Or, it's not just about X, it's about Y. LLMs dramatically overuse this specific rhetorical structure because it creates the illusion of balanced, thoughtful analysis.
It assumes the reader has an incomplete or naive thought, and it wants to correct it. It's not just about the beat writing under the vocals, it's part of the raw aggression.
And closely related is the rule of three padding. The AI will chunk things into groups of three just to sound comprehensive.
Our software is fast, secure, and reliable.
Designed for global SEO professionals, marketing experts, and growth hackers. It is rhythmic filler.
We also absolutely must eradicate the outline-like conclusions.
Oh, if you have ever used an LLM to generate a blog post or a white paper, you know exactly what this is.
You ask it to write an objective analysis, and the very last paragraph inevitably starts with the phrase, "Despite its challenges," followed by a vaguely positive, sweeping assessment of the future.
Despite the challenges facing the global supply chain, future investments in technology could enhance its efficiency and foster a new era of growth.
It reads like a high school essay conclusion. It is rigid and formulaic.
And finally, on the structural side, we have false ranges.
A false range is when the AI uses the from X to Y structure without providing an actual literal scale or spectrum.
A human writer uses this structure for physical or literal extremes, from head to toe or from freezing to boiling.
But the AI tries to use it poetically and it fails. It will write, "Our journey has taken us from the singularity of the Big Bang to the grand cosmic web."
Or it represents a shift from problem solving to artistic expression. There is no actual continuous middle ground between those two things.
It is a false hallucinated range.
Okay, so that covers the stylistic grammatical scrub. But our Wikipedia source guide goes even deeper. We have to address the technical tells.
Formatting errors, markdown quirks, and outright system hallucinations. If your product outputs these errors to a client, you are dead in the water.
This is the forensic code-level scrub. First, markdown leaks.
AI chatbots natively format their text using a language called Markdown. They use asterisks to create bold text, or hash symbols to designate headers.
Frequently, especially if you are passing AI data through an API directly into your product's user interface, that raw markdown syntax leaks into the final client-facing text.
You have to run scripts to scrub rogue triple backticks that surround code blocks. You have to watch out for the AI's tendency to put excessive boldface on every single key term in a paragraph.
You also need to correct title case headers. AI models have a strong, persistent habit of capitalizing every major word in a section heading.
They also have a structural quirk where they skip heading levels entirely. They will format a document with a level 1 heading and then jump straight to a level 3 heading, skipping level 2.
Oh, and watch out for curly quotes. Models like ChatGPT and DeepSeek natively prefer using curly slanted quotation marks and curly apostrophes instead of standard straight ones.
It is a microscopic detail, but to a trained eye, it is an instant tell.
But the most dangerous technical leaks by far are code artifacts.
Due to complex software bugs and how these models process live web searches or internal reference documents, they will occasionally spit out literal strings of back-end diagnostic code right into the middle of a sentence.
The sources provide the exact strings you need to hunt down in your database. You must run a search for turn 0, search 0.
This artifact appears when the AI attempts to link to an external website, but the link breaks during generation, leaving the back-end placeholder exposed to the user.
Imagine a client paying a premium for your report generator, and the final page says, revenue grew by 20%, turn 0, search 0.
Your credibility is destroyed.
You also need to query your database for strings like oesite.0 or content reference or attached file.1.
And crucially, you must check your outbound URLs for fake UTM tracking parameters that the AI injects automatically, like adamsourcechatgpt.com.
If an enterprise customer clicks a link inside your proprietary app and sees chatgpt.com in their browser URL string, the curtain's pulled back.
The illusion of your proprietary deep learning engine is just gone.
And if your premium feature involves doing research, summarizing documents, or generating reports, you have to be vigilant against citation hallucinations, specifically fake DDoI's digital object identifiers.
Because of how the model predicts the next statistically likely token, it understands the format of a valid DOI perfectly.
It will generate a string of numbers that looks completely real. But when a client clicks it, it leads to a completely unrelated scientific article.
The source material provides a wild, terrifying example of this. A user asked an AI for information, and the AI confidently cited a 1967 physics paper by a scientist named C.L. Fortescue regarding Ohm's law.
The DOI was formatted perfectly. It looked absolutely real.
But the DOI actually pointed to a completely different paper about Chinese history.
Furthermore, there was no paper written in 1967 by C.L. Fortescue about Ohm's law. In fact, C.L. Fortescue died in 1936.
The AI had statistically woven together a real formatting structure, a real historical name, and a real scientific concept into a totally fabricated hallucination.
It will also generate book citations, but conveniently hallucinate the page numbers, making verification impossible.
Or it will declare list-defined references in the back-end code, setting up a bibliography, but then forget to ever actually use those citations in the body of the text.
And finally, the last thing we must scrub in Phase 4 is conversational bleed.
This occurs when the AI momentarily forgets that it is supposed to be a seamless back-end processor for your product, and it reverts to its baseline training as a helpful customer service chatbot.
As an AI language model, I hope this information helps you with your project.
Or it injects speculative, defensive knowledge cutoff disclaimers, as of my last update in January 2022.
Or, while specific, real-time details are limited in the provided sources, it is defensive filler.
You must write aggressive system prompts that strictly forbid the model from ever outputting conversational meta-commentary about its own nature.
Okay, I have to push back here. Let me play devil's advocate for the listener who is looking at this massive hit list.
Let's hear it.
Some of this just sounds like formal, highly educated, slightly stiff writing.
Right.
If I have a human product marketing manager who naturally writes the word crucial in a or uses perfect grammar, or deploys the phrase seamless integration, are we accusing them of being a bot? Are we saying humans are no longer allowed to use formal vocabulary?
That is a critical distinction, and it is vital we get this right. Perfect grammar, correct spelling, or formal registers alone are highly ineffective indicators of AI text.
Many professionals write formally.
The point our sources emphasize, and the core philosophy of this scrub, is that it is the cluster of these specific quirks that reveals the machine.
The density.
Exactly. If a human writer uses the word crucial in a white paper, that is perfectly fine. But if that same white paper uses crucial, rich tapestry and delve in the exact same paragraph,
while simultaneously avoiding the word is,
deploying a negative parallelism like not only fast but secure, and accidentally leaving a turn zero search a markdown tag at the bottom of the page.
that is not a human with a formal vocabulary. That is a large language model.
It is the clustering of the vocabulary, the structural tics, and the technical leaks that exposes the automation.
The cluster. I love that. So the scrub is complete. You have subjected your entire product experience to the Dieter Rams philosophy.
Utility first. No fluff. No false ranges. No elegant variation. No citation hallucinations. Which brings us to the finish line of our mission.
Day 30, the validation loop.
Day 30 has arrived. Let's review the asset. Your product is structurally sound, moving from cost to revenue based on phase 1.
You thoroughly understand the deep learning math, the activation functions, and the financial levers of the architecture from phase 2.
It is beautifully prompted, with studio-quality aesthetics and targeted marketing from phase 3.
And it is rigorously, forensically scrubbed of all cheap AI tells from phase 4.
It is time to launch.
And here, we must circle back to the absolute core directive of the manifesto we started with. Ship the constrained version. Put it in front of real customers.
Do not wait 6 months to try and build the perfect, all-encompassing, generalized platform. Ship the specific targeted feature today.
And understand what you are measuring. The goal on day 30 is not to track daily active users.
It is not to track vanity metrics like how many times someone clicks the new AI button.
The singular goal of this entire 30-day sprint is to test willingness to pay.
That is the only metric that matters.
Because internal efficiency using AI to save money on the margins of your operations counts very, very slowly.
But a revenue-generating feature.
A feature that clients look at and say, yes, I will pay a 20% premium for that capability. That fundamentally reshapes your entire business.
It changes your positioning in the market, it drastically increases your pricing power, and it alters how investors and competitors perceive you.
So here's the final challenge to you, the listener, the ambitious builder.
Review your portfolio today. Identify that one CU, that one feature, or that one service where an embedded deep learning architecture can introduce a higher pricing tier.
Find the spot where it can increase your ARPU average revenue per user through a direct, undeniable upsell.
Or where it can create a brand new usage-based revenue stream that didn't exist yesterday.
30 days is enough time.
It is enough time to architect the engine, build the assets, scrub the tells, and prove to the market whether your AI strategy is a slow cost story or an explosive revenue story.
We just took you on a massive journey.
From the initial mindset shift of treating AI as true capital, through the biological mimicry of hidden layers and backpropagation.
Into the Michelin star prompting frameworks.
And finally, through the rigorous DRAM's quality assurance process.
It is a complete end-to-end playbook for validating a new line of revenue.
But I want to leave you with a final provocative thought. Something to chew on as you log off and start building this.
Let's hear it.
We just spent an immense amount of time and energy over these 30 days painstakingly building, prompting, and scrubbing an AI product specifically so that human beings will perceive it as a premium asset and be willing to pay for it.
We scrubbed the idiolect, we hid the tells, we tailored it for human psychology.
Right. But what happens in 2 years? What happens when your B2B enterprise customers procurement department isn't staffed by humans anymore?
Oh, wow.
What happens when they stop reading your white papers and instead they deploy their own AI agents to negotiate the contracts, evaluate the software architecture, and decide if your AI product is actually worth paying for?
When an AI is selling directly to an AI.
Exactly. When a procurement bot is analyzing your seller bot, will any of these human tells even matter anymore?
Will the AI buyer care if your marketing copy used the word tapestry? Or will it completely bypass the interface and just read the raw API efficiency and the mathematical loss function?
Suddenly, that broken X-ray sorting machine we talked about in phase 2, it might just be two deep learning machines looking at each other in the dark, communicating in vector space, deciding what financial value even means.
That completely changes the landscape of commerce. It removes the human aesthetic entirely.
It really does. But until that day comes, the humans hold the wallets, and the humans demand premium quality.
True.
Thank you for joining us on this deep dive. Get out there, build that new storefront, and test that willingness to pay. We'll catch you on the next one.